Recently, Huawei released something new. Dow law. The original report reads it this way. What is the Dow law? What is logical folding? What is Moore's law? It feels awesome, but it's a bit hard to understand. And there's a more practical issue. Rely on it. Can we really bypass lithography machines? In response, I can't make a judgment. That still depends on time. Let's see how the chips perform next. But at least, what exactly is Dow? Let's get a general idea first. I did some homework for this. We also studied the original papers of Huawei and Tingbo. Of course, 4 plain science explanations. Some aspects have been simplified to the point of being inaccurate. Real chips are 10,000 times more complex than this. So if you have any additions, feel free to let me know in the comment section. 1. Moore's law. It's not a scientific law. This is industry consensus. We need to clearly explain the Dow law. First, we need to clarify Moore's law. Why? Because Moore's law has reached its end. Only then did the Dow law take the stage. Moore's law. It was founded by one of Intel's founders. Moore suggested the first year is the number of transistors on the chip. It roughly doubles every 2 years. While performance has greatly improved, prices will also be available during the day. But you might not know, Moore's law is not a scientific law verified by experiments, but rather a summary of experience. Just like you discovered, the neighboring child grows 5 centimeters taller every year. The next few years will probably look the same. Since this is just a summary of experience, why can it dominate the industry for 60 years? Because it lowers one thing: internal friction costs. Thinking about it, without Moore's law, the design firm said, I think the density will increase by 50% next year. The manufacturer said, at most, I can make 20%. Equipment vendors say it's all wrong. I estimate 25%. The result was the chip designed for this purpose. Manufacturers can't produce it. But with Moore's law, the entire industry has a shared expectation. The number of transistors will continue to grow rapidly. So the design company, manufacturing plant, the equipment moves in the same rhythm. Internal friction has been greatly reduced. The true value of strategy is reducing internal friction. Moore's law. This has been the core strategy of the semiconductor industry in the past. So what is the core approach to achieving this strategy? Make the transistor smaller. The key tool is the lithography machine. But this path has come to this point. It seems to be the end. What does that mean? Physically, it was pushed to its limit. A silicon atom is about 0.22 nanometers long. Meanwhile, the process for cutting-edge chips has already reached the 1 nanometer node. On such a small scale, the electronics also obeyed either. It passes directly through the transistor switch, making control increasingly difficult. Financially, it has also reached its limit. The paper provides a detailed description. The design budget for cutting-edge chips has already exceeded $1 billion per chip, and in the most advanced manufacturing processes, the cost per transistor has stopped decreasing. As a result, the industry fell into confusion. Transistors can no longer be made smaller. Next, we should take it to fixed rate of extraction. How small can you be without asking? Asked how much longer he could wait, Huawei said, I have an answer. Fixed rates. To put it plainly, it's a simple translation. Improving performance by shortening latency. It's no longer just about making the transistor smaller. What does that mean? Over the past few decades, the industry has always been doing one thing: make the transistor smaller. But make the transistor smaller. Actually, that's not the goal. It's just a means. Transistors become smaller. Switching speed is faster. Signal distance is shorter. Lower transmission latency. Finally, it affects the experience, not the small ones themselves. It's about reduced latency. So you really need to have something to say. These are various delays within the computing system. Delay in circuit signal propagation. Delays in moving data from storage to computing units. Communication delays between multiple chips. Each one is a loss of performance. So Huawei did something. Spread the delay across different layers, unified and abstracted into a single indicator. And that's how Dow made his entrance. The core goal of the Dow law: it's just compression latency. How to do it? If you only look at the circuit layer, there is a core bottleneck. This is called RC latency. R is resistance. C is capacitance. What is resistance? Resistance can block the current, just like the thickness of a water pipe. It affects the speed of water flow. The finer the pipe, the slower the water, the greater the resistance, the more difficult it is for current to pass through. What is a capacitor? Just like buckets used to store water. Signal transmission delay. You can roughly understand it as waiting time to fill the bucket with water. Water pipe system. The bucket is big. Naturally, the delay is significant. Therefore, the circuit layer reduces latency. The solution is straightforward. Or lower the resistance, or lower the capacitance. Here's how to do it. In Huawei's paper, a core direction has been given: logical folding. 3. Logical folding. Shipbuilding from single-story houses into multi-story buildings. What is logical folding? Imagine an office building. If the entire company's department all crowded on the same floor, the marketing department should find the product department. The product department contacted the R&D department. Every communication had to be crossed by a long corridor. All the time was wasted on the road. But what if you change the design? The marketing department is on the first floor. The product department is on the second floor. The R&D department is on the third floor. The originally over 100 meters of lateral distance. Only a dozen meters of stairs remained. This is the logic of folding logic. Stack the originally flat circuits. The signal doesn't have to run sideways for a marathon. Just walk upright up the stairs. The path is short. Resistance drops are unlimited, side by side, and less. Latency is naturally compressed. So, how effective is this method? And Tingbo's paper gave two numbers. Density increased by 55%. Energy efficiency improved by 41%. This might be indicated. Huawei has already taken its first step on this path, but Huawei's goals go beyond that. By 2031, it aims to reach an equivalent 1.4 nanometer manufacturing level. 4. Equivalent to 1.4 nanometers, not physical dimensions. It is the overall level. What is the equivalent of 1.4 nanometers specifically? From Huawei's perspective, I don't necessarily have to make the transistors that small, but by logically folding these methods, I can bring the overall level close to the 1.4 nanometer node. Let's use office buildings as an example. Traditional route. It's on the first floor. Make each office smaller and smaller. This way, one floor can fit even more people. But the fixed rate route is key. The size of this office remains unchanged, but the office building was changed from one floor to multiple floors. It's the same piece of land. The floor is higher. There are actually more rooms available, but achieving this is not easy. Obstacles on the road appeared one after another. The first tool issue. Today, the chip industry is designed for software. Most of them were factory goods from the single-story era. The software assumes you are building a floor. Now suddenly you say, I want to build a building. Machine rooms, elevators, pipelines, all of these are optimized together. Originally, having too many tools was no longer enough. The second process issue. In theory, it can be stacked. This does not guarantee stable mass production in reality. And built a single-story house. Construction errors are easy to control, but building a tall building has become much more difficult. More importantly, the floor has become taller. The stairs themselves also take up space. The vertical interconnection structure inside the chip. It doesn't just take up space. It also brings additional resistance and capacitance, making manufacturing more complex. Liang led the way up and did not leave. The cost is so high that it can't be commercialized. The third issue is energy consumption and heating. Transistors stacked up. Power consumption and heat generation per unit area both increase sharply. The heat dissipates but does not escape. The chip will overheat and slow down. There is a particularly insightful line in the paper. Tao is the law of time, not the whisper rule. Simply put, speed doesn't mean saving electricity. So compression delay is a matter of compressing. You can't just judge by speed. It also depends on whether it's worth it. If it's just for speed, turn the system into a power-hungry monster. That would be invalid commercially either. So you can see the real difficulty of this path, not in any particular technique. Instead, it is about reshaping the entire engineering chain. Design tools need to be redone. Manufacturing processes must keep pace. Energy consumption needs to be balanced. Even testing standards may need to be revised. It's not easy. The goal for 2031. Huawei still needs to verify step by step. Finally, back to the question everyone cares about most. Can we really bypass the light with it? The answer is still unknown because of the real business world. Just by proposing a concept, you don't win. It still needs to be implemented. To verify, promote it on a large scale. It depends on the actual effect. Heat dissipation, Liang Shui, software ecosystem, and so on. Every obstacle. Behind it are massive amounts of capital and engineers. Until these problems are resolved, it is too early to draw any major conclusions about success. So in the face of the current debate, we can maintain maximum rationality and restraint. But the road ahead is long and winding. Its cultivation extends far to the west. Do not seek what is above and below. Best wishes to Huawei. Follow Liu Run, lowering the cognitive barrier for business.